Cayley-Hamilton theorem. A very basic fundamental theorem in matrix algebra. If A is n by n, determinant of A minus lambda I is P of lambda, roots of P of lambda are eigenvalues of A, as you surely know, but what this theorem says is that P of A is equal to 0. This is a matrix here. So, for example, if P of lambda is equal to lambda square minus 2 lambda plus 13, then what we mean is A square minus 2A plus 13I is equal to 0, where this I is the identity matrix, just like this one. Okay. Now, if A is n by n, then this will of course be an nth order polynomial. This quadratic is just a hypothetical example. Let us see how it works out in Maple. So, I'm starting again with Maple, and then I will say with lin alg to warn Maple that I will want some matrix calculations. I will say A is equal to matrix. I will have to put some arbitrary numbers to show you, but I will these are numbers I find easy to remember. That's not actually a 0 in, but other than the last one, these are numbers from pi, so I remember that. Now, we can do things like the determinant of A, and it will give us a number. We can do things like that in Maple, but I will come back here and I will now put lambda, and here minus lambda, and here minus lambda. I am still calling it A, but this is actually now A minus lambda I. I take the determinant, and that is what I get. Okay. So, I can say I can say eval f solve the previous for lambda, and it will give me 3 roots. Okay. It gives me this very small imaginary part. Don't worry about it. The roots are real. 11.56 minus 6.14 and 2.58. I can come here and I can say A equals 314,159,270, and then I can say the eigenvalues of A. I will get the same. This is MATLAB. Okay, 11.5, 2.6, 2.58, 6.14, same roots. Okay. Now, what is more interesting is over here I have minus lambda cube plus 8 plus 57 minus 183. So, let us come here, and I have minus 8 times A times A plus 8 times A times A plus 57 minus 183 plus 57 times A minus 183 times I3. Okay. All right. 0. Okay. So, it satisfies its characteristic polynomial. Let's try to understand why this happens. So, in most cases, you see, so suppose A phi is equal to phi lambda, and this is diagonal, and this is invertible. This is called the eigenvalue decomposition. It's not always possible. So if A is not symmetric and it has repeated eigenvalues, then I may need something called Jordan canonical form, and I am avoiding that here. Okay, there are good reasons for that. The vast majority of matrices have an eigenvalue decomposition, and even that matrix is very, very sensitive in the sense that if you perturb it infinitesimally, then the eigenvalues become distinct, and then this is possible. So for our purposes, this is good enough. Okay, so what this means is A is equal to phi lambda phi inverse, which means A squared, which is A times A, is equal to phi lambda phi inverse phi lambda phi inverse, which is just phi lambda squared phi inverse. And now because this is diagonal, therefore this is also diagonal. So for example, if this is lambda 1, lambda 2, lambda n and all zeros, then this is lambda 1 square, lambda 2 squared up to lambda n squared. Okay, and it is for this reason that when suppose p of lambda is equal to a0 plus a1 lambda plus a2 lambda squared plus dot 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 plus an lambda n, this an will be plus or minus 1 the way we have written it. It doesn't matter. Let's just think of it as a number. In that case, p of a is understood to be a0 I plus a1 phi lambda phi inverse plus a2 phi lambda square phi inverse, and so on. And then you see what you can do is you can take this coefficient, not this, take this coefficient and absorb it into the diagonal, take this coefficient and absorb it into the diagonal, and when you do that, then this one comes out to the left, this one comes out to the left, that one goes to the right, that one goes to the right, and this can be interpreted as phi inverse. There is no problem. And as a result, what we get is phi a0 I plus a1 lambda plus a2 lambda square plus dot 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 plus an lambda n phi inverse. And now these are all diagonals, you see, and so each diagonal element is now just becomes phi, and then we have p of lambda 1, p of lambda 2, p of lambda n 0 0 phi inverse, and then that is equal to phi times all 0 0 0 0 phi inverse, because in fact these lambdas are the roots of the characteristic polynomial. It is for this reason that we have every square matrix satisfies its characteristic polynomial. You may wonder what happens when it does not have independent eigenvectors. One way to think about it is to perturb it very, very slightly so that it does have independent eigenvectors. And now the characteristic polynomial is just a continuous function of the elements of A, and so there is a very small change in it, right? And so therefore now a very slightly perturbed version satisfies, you see, so it becomes 0, and then you sort of take the perturbation to 0, and then it just 0 0 0 0, limit is 0. In this way you can think of a continuity argument, but I am not going to beat it to death. We will stop here. So the Cayley-Hamilton theorem for purposes of our class is now established.